Deep learning is a fascinating subset of machine learning, inspired by how the human brain works. Here's an AI-generated image. What do you see at first glance? It's a sunny day and a crowded beach, right? Upon closer inspection, we see children playing in the sand around a massive sand castle at the center. We then examine each person on the beach more closely. We find that AI rendered this individual's face oddly, resulting in a bizarre and slightly unsettling appearance. Our brain processes information in various phases and at varying depths. Initially, viewing an image provides a raw, broad impression that presents insights into the scene's context. The more time and attention we devote to details, the more information and subtleties we can process and observe. In the context of deep learning, a neural network processes information similarly. Here's what a neural network resembles. Please don't be scared. Everything will make sense in a second. Picture the first layer as our input information, similar to observing a sunny, crowded beach day. Then, as the data passes through more network layers, intermediate layers start recognizing more complex features, such as shapes or specific objects. Remember how I noticed the enormous sand castle in the middle? Every intermediate layer of the neural network builds a more detailed understanding of the basic features identified by earlier layers. So there's an incremental increase in the level of detail acquired. The deeper layers of the network synthesize lower-level features into high-level features, representing more complex aspects of the input data. This is how we can spot the strange face generated by AI. It took some time to process the information and get to this conclusion. Honestly, I think I subconsciously wanted the picture to reflect that because I was curious if the AI had produced a quality example. And eventually, my brain focused on this little detail. Okay, perfect. So that's the intuition behind deep learning. It's a complex process that allows machines to learn by processing input information in stages. Let's explore some technical details to deepen our understanding. We call this neural network artificial neural network, or ANN. Biological neural networks inspire it, but they work much differently. Like our senses, an ANN's input layer sends raw data to the brain. Then the intermediate layers, or hidden layers, process input information. Neural networks can have one or multiple hidden layers. Increasing layers enhances complexity. Adding more layers to a network increases its learning capacity, but the downside is that it needs to be carefully managed to ensure effective learning. We also have an output layer that generates the final result. Every layer of the artificial neural net is made of neurons, or nodes, responsible for processing and transforming the information received. If you recall, I previously referenced the MNIST example in one of our lessons. We noted that training a model to recognize handwritten digits involves supplying it with thousands of pre-labeled examples. How does this training happen? While the process may initially appear complex, let's simplify it to a more manageable form. The process starts with the input layer of the ANN receiving an image of a handwritten digit. Each pixel of this image serves as an input node. In the case of MNIST, images are 28 by 28 pixels, so the input layer typically has 784 input nodes. Imagine that the 784 input nodes are stored as a vector inside the neural net to form the input layer. Each of the 784 input nodes contains a number based on how bright or dark it is. Here, 0 represents white, while any value greater than 0 indicates a color other than white. We call this number activation. The higher the number, the darker the content inside a given node. We describe the 784 input nodes in the input layer as the neural net's width and its number of layers as its depth. Here, the network comprises 3 hidden layers along with the input and output layers, totaling a depth of 5. We have numerous connections between nodes because each layer's nodes are linked to every node in the subsequent layer. This extensive network of connections is essential for learning from input data, serving as mathematical transformations. These transformations occur through a mix of weights and nonlinear operations, with optimal weight combinations across all nodes enabling learning. This method translates the input via various layers, refining the information before it generates a result. Learning occurs by designing a system that identifies optimal weights and biases to solve a specific problem, involving thousands of repetitions to discover the best combination. So, why do we need several layers? What kind of transformations can we expect in each layer to end up with a system capable of recognizing the digits in a photo? Well, when we see an image in the background, our brain connects various components of what it is made of. For instance, the number 3 comprises 2 elements, a rounded top and a curved bottom. The first hidden layer in our neural network might learn to recognize these features from the input data. Then, in the second hidden layer, we continue to build on the information processed by the previous one. We've identified edges and curves, and now we can use them to discern more complex shapes, like loops and intersections, bringing us closer to recognizing numerals. When the information reaches the third layer, the neural network has learned to recognize the overall shape and configuration representing the number 3. Finally, the output layer takes the processed data from the last hidden layer and determines whether the digit is a 3. This is how a neural network learns to perform what appears to be a simple task, recognizing a number. The underlying process, however, involves intricate mathematical manipulations, which we didn't describe fully. In essence, the layers of an ANN, through their depth and breadth, create a robust system of pattern recognition and data interpretation that mirrors some aspects of human cognitive processes, albeit more structured. This capability to analyze large, high-dimensional datasets and recognize complex patterns with high accuracy makes deep learning a revolutionary tool in AI. It's what has made today's incredible AI advancement possible.